Okay, chapter 4 is about the postulates and general principle of quantum mechanics. So before we start our lecture, let's think about the English expression postulate. So this is very academic verb. Academic language. So we haven't used this terminology usually in our daily life. So when you search the dictionary, it says that the postulate is a statement or assumption that is accepted as true without proof, usually because it is considered self-evident or serves as a starting point for reasoning. So it is a kind of assumption with a like well-educated assumption. So it is not just like, oh, let's assume like this. So it is more about based on the many physical observation, we think that this might be true. So you can accept the postulate as the background of some subject. So in our case, we are going to review 5 postulates. That is the background of the quantum mechanics. So in the last section, we traced the historical breakdown of classical physics, the ultraviolet catastrophe, and various experiments. And this failure of the classical physics lead us to the quantum mechanics, which investigates the very tiny world, the microscopic world, such as the electron, atoms, and molecules. So we now understand that the Schrödinger equation is the governing equation of the quantum mechanics, like the very small scales world. But there is one crucial question that still we have to answer, is that where does the Schrödinger equation come from? Like, do we have to accept that as a solid truth, or is it just a small part of some big world of the quantum mechanics? So in this chapter, we are going to address that question. So we are now moving from solving specific problems, like as we did in the chapter 3. We solved the particle in a box problem, but now we are trying to understand the fundamental rules of games, like quantum mechanical games, for how the equation and operator things come from. So just as classical mechanics that is built upon the Newton's mechanics, so we are going to try to understand that quantum mechanics is built upon a set of core principles known as postulates. So these postulates are, in a sense, just a conjecture about how the universe operates at the most fundamental level. So they provide a logical foundation for everything we have done so far, like the mechanism of operator, how the operator works in the mathematics way. And we also discussed the wave function. So wave function, operator, and how these are related to the physical observables. Okay, so this chapter is more about the concepting. So if you understand this chapter very well, then when you go back to chapter 1 to 3, then you feel more comfortable with mathematical calculation. So let's discuss the wave function first. So when you study the physics, we always begin by a fundamental question: how do we describe the state of a system? So in the classical mechanics, you know that the Newtonian's equation. Newton's law. So the state of a particle is defined by its precise position vector, and the velocity at the specific moment. So when I use this double line, this is usually denoted vector. So if you know the position and the velocity, then you can with initial condition, then you can predict its exact trajectory for all future times using Newton's equation, which is known as F equal ma. So however, as we enter the microscopic world of electrons, atoms, and molecules, this deterministic picture breaks down. So we called the Newtonian mechanics as deterministic picture, which means with given condition, position, velocity, and initial condition, we can predict its exactly accurate trajectory. So it is already determined. But the Heisenberg uncertainty principle in quantum mechanics uncertainty principle. So this principle tells us that we cannot know both the precise position and the momentum simultaneously. So this requires a completely new way of describing the state of a system, which brings us to the first and the most central postulate of quantum mechanics. So postulates number 1. So I'm going to write down the whole statement because this is very, very important. The state is defined by the wave function. So the first postulate of quantum mechanics states that the state of quantum mechanical world or the system is completely described by a mathematical function called wave function, usually denoted as psi, with its variable position r and time t. So this postulate claims that knowing this function, psi, you can calculate nearly every property of that system. But we have to discuss the physical meaning of the wave function psi. So unlike position or velocity, the wave function itself is not a directly measurable quantity. So there is no experiment that can directly capture this wave function. So when does the significance of the wave function come out? When do we realize that the meaning of the wave function? The physical interpretation of the wave function can be realized when we take the magnitude of the wave function and take the square of that magnitude. So according to Max Born, this quantity represents the probability density of finding some particle at that specific position and given time. So if you have this quantity, the square magnitude of the wave function, that means the particle is likely to be found at that specific position at the given time. And where it is very small, that means the particle is unlikely to be found at that position. And so far, we haven't discussed the feasible candidate or wave function. So we are going to discuss some requirement. So you might want to say maybe every function like f equal x or f equal x squared can be a wave function. But unfortunately, they cannot be a wave function for any system. So let's discuss why. So according to the interpretation of Max-Born, the square of the magnitude of wave function represents the probability density. So somehow the wave function is related to probability. So for this probabilistic interpretation, the wave function must be well behaved. So there is a notation, quote notation. That means it is not really scientific, but we use that expression so many times in quantum mechanics. So let's find out what the well-behaved wave function is. So as I mentioned, the interpretation of the wave function is related to the probabilistic interpretation. So there are 4 conditions. The first one is the square integrable. So that means if you take the square of the wave function, it should be integrable. That means you can evaluate the integral of the square of the wave function. So if you cannot integrate the square of the wave function, or let me correct my expression. So if you cannot integrate the square of some function, then those function cannot be a wave function. Okay? Because the particle must exist somewhere. So the sum of the probabilities over all of the space should be what? Should be what? Should be 1, right? So we integrate all the possibilities over the world or the universe, then the probability of finding the particle at somewhere in this universe should be 1, right? So that means we need to calculate the probability and right. So the first condition is we have to be able to integrate the square of the function. And the second point is single valued. So at any point in space and time, there can only be one unique probability of finding the particle, right? So if you want to have some function like x equal 1, t equal 5, if these function have multiple values like 2 or 3, then the square of this function should be related to the probability of finding the electron or the particle. So should it be 4 or 9? So it doesn't make sense, right? So the finding the particle at specific position should be given as a 1 value. So like this multiple valued function cannot be a candidate for a wave function. So true wave function should be single valued at any position. And the third point is the function should be finite. That means the function should not go diverge to the infinity. It is also consistent with the first condition because we are dealing with the probability density. That means the infinite density doesn't make sense, right? So the function should be finite over the whole region. And the last, the function should be continuous. So both the wave function and its first derivative must be continuous. So f and f prime, which denotes the first derivative of the function, they both of them should be continuous. So if there is a break or sudden jump in the wave function, that means the second derivative, if you have discontinuous f, then that means the f double prime, which is related to the kinetic energy, so this goes to the infinity if there is a discontinuity. So infinite kinetic energy doesn't make sense, right? So energy should be conserved and energy value should be finite value. So we cannot accept the infinite kinetic energy. That means that this continuous function should not be a wave function. Okay, then let's move on to the next section. So section 4.2 is quantum mechanical operators represent classical mechanical variables. So we already figured out this correspondence, the quantum mechanical operator and classical mechanics variables. Yeah, we already discussed that like chapter 3, I guess, when we discussed the operator. But we are going to take a look at some condition for the operators to have a correspondence with the classical mechanical variables. So now we have postulates that the wave function, you can extract any information of that system from the wave function. So that is our first postulate. And if you want to extract some information from the wave function, then you are going to use the operator, right? The operator is a tool that extracts information from the wave function. So postulate 2. So to every observable in classical mechanics, there corresponds a linear operator in quantum mechanics. So this is exactly what we discussed in the chapter 1 or 2, maybe 3, right? When we discussed the operator. So there is a correspondence between the classical mechanics observable, which means the quantity that you can measure, and a correspondence between the observable and the linear operator. So maybe then later in this class, we are going to put another condition for the operator to have a correspondence with the classical mechanics observable. That should be placed somewhere here, linear Hermitian operator. So that should be the revised postulate, the second postulate. But for now, we are going to just focus on the linear operator. So observable is simply any property of the system that can be measured. So for example, so let's think about the angular momentum. So this is a key observable in rotational motion, defined as the cross product of the position vector r and the linear momentum vector p. So this is just like the angular momentum is usually denoted as L. So as you can see here, the angular momentum is the vector quantity. That means it has 3 components. So it consists of Lx, Ly, and Lz. That means the angular momentum component of along each axis, x and y and g axis. And each component can be calculated using this relation. So let's just. I'm not going to write down whole 3 equations, but they look very similarly. So according to postulate 2, to find the angular momentum of a quantum particle, we can no longer use just this classical expression. So instead, we have to find and construct the operator that can extract the angular momentum from the wave function. So that should be the angular momentum operator in the x-axis. So we are going to denote that operator using Lx hat. So the second postulate provides the recipe for turning classical variables into mathematical tools called operator that we can use to interrogate the wave function. And now we understand the role of operator in quantum mechanics, but still we have to discuss the physicality or the physical meaning of being linear. So let's take a look at this example. So if you have an arbitrary operator A hat, and if you have a measurement related to this operator, you always have a value small a. So if you want to write down the mathematical expression for measuring the quantity related to operator A, always gives a, small a, then it should be written as a hat psi equals small a psi. So it is the form of eigenvalue equation. So now we consider a situation where 2 different states, psi 1 and psi 2, both yield the exactly same measurement value small a. So if you have a system like psi 1 and psi 2, they are different, but both of them gives the same measurement small a hat psi 2 a psi 2. What is the terminology for describing such a situation? Two different wave functions correspond to identical eigenvalue. We called this degeneracy, right? Degeneracy. It's because the operator a hat, this one is linear, right? We postulate that the quantum mechanical operator should be linear. So we can prove that any linear combination of the wave function psi 1 and psi 2 is also a valid state that will have the same eigenvalue. Okay, so if you take the linear combination of psi 1 and psi 2, which is our degenerate, so their linear combination should be something like C1 psi 1 plus C2 psi 2. So this is also the eigenfunction of the operator A with the same eigenvalue. So let's take a look at this statement is true. So if you apply the operator A to the linear combination of psi 1 and psi 2, so that function should be something like this. So we postulate that this operator A should be linear. That means we can take out these constants C1 and C2 out of the operator. And you can apply the operator to each function first. So that means C1 a hat psi 1 plus C2 a hat psi 2. So according to the characteristic of linear operator, these two sides should be equal. This is because of the linearity of the operator. So you apply this operator to the function, then we already know that psi 1 and psi 2 are degenerate with the eigenvalue A. That means you are going to have a C1 small a psi 1 C2 a psi 2. And the constant a is common in both terms. So if we take the group using a, then C1 psi 1 plus C2 psi 2. So both a and the constants C1 and C2, they are just number, right? So the ordering of the multiplication is not really important. So that's why we can take out a. So now it is just the final result. So let's denote the linear combination of psi 1 and psi 2 as the capital psi. Then a hat capital psi is equal to what? So there is equality, and this equals to small a multiplied by capital psi. So now we see that if you have a wave function, two different wave function with the same eigenvalue a, their linear combination also has the same eigenvalue. So this is the very basic, and this is the fundamental principle of the superposition. So if there is a many different wave function with the same eigenvalue, they can like mixed up together. But there are many different states. So when we take the measurement, we might encounter two very different observable. Okay, so yeah, section 4.2 is about the condition for the operator, and let's move on to the next section. Section 4.3, the title is Observable Quantities Must Be Eigenvalues of the Quantum Mechanical Operator. So that means that if you take the measurement, then the number that you are going to obtain is always the eigenvalue of that wave function. Okay? So let's go directly to postulate number 3. I reuse the Ch4 for the postulate. So when we measure a physical property in any single measurement of an observable associated with operator A hat, the only value that will ever be experimentally observed are the eigenvalue A, which satisfies the eigenvalue equation A hat psi A. Yeah, this is quite long statement, but you always have to remember some keyword. So if you take the single measurement, so you can count like the position, momentum, or energy single measurement that associate with operator A. And you will going to only observe the quantities that is the eigenvalue small a. So it is not possible if you take the single measurement, then you have the some value outside of the eigenvalue. That is not possible, right? So, but still this is possible. Like if the wave function psi that has some set of eigenvalues, right? It is still possible. So the set of eigenvalue. So this is called the spectrum of the operator. So I don't really want to say that the wave function should be correspond to the single eigenvalue. So if you go to the particle in a box problem, the wave function given as the square of 2 over a. Let's use the L. So we don't want to confuse ourselves with the eigenvalue and the length of the box. So one-dimensional wave function, wave function for a one-dimensional box should be given as this. And this function has some set of the eigenvalue for the Hamiltonian operator. Something like this, right? So we now have some set of the eigenfunction, and we have the set of eigenvalues. So this set of the eigenvalues forms a spectrum of the operator. So let's continue our discussion using the particle in a box problem. So if you take the measurement of the energy for the one-dimensional box, then the only energy that you can measure is just like h squared over 8 ml squared, or 4h squared over ml squared, or something like this. So we already discussed and emphasized that we cannot measure the value in between these two quantized energy levels. 3h squared over 8 ml squared, this value cannot exist. So particle with that energy cannot be present in the particle in a box. Okay, so you always have one value among the spectrum set of your operator. Okay, then let's move on to the postulate number 4. So the first postulate is about the average of many measurements. Average of many months. So postulate number 3 tells us the outcome of a measurement if the system is a perfect eigenstate. But what if the system's wave function psi is more complex? I mean, the superposition of many different eigenstates. So in this case, we cannot predict the outcome as a single measurement with certainty. But still, in this case, we can predict the average result from a very large number of measurements on identically prepared system. So for the energy, so when it doesn't really matter how many times you take the measurement for a particle in a box problem. So you always have the number for like this, and this. But what if you take the measurement of the x position of that wave function? So if you think of the particle in a box problem, even in the ground state, the wave function looks like this. So maybe you can find some particle at here at the first measurement. Maybe second measurement you will find the particle at here. Maybe third measurement, particle will be here. So your wave function is not the eigenfunction of the x position operator. So that's why you always have, not you always, you might have different numbers for the x position in the series of x position measurement. Okay, but so then you might think like, oh, we cannot say anything about the the position, because this is not the eigenfunction of the X operator. But the postulate 4 says that even though we cannot get a single value for operator that is not corresponding to the wave function, I mean the eigenfunction, but still you can get the average value of that operator. So postulate number 4 is if a system is in a state described by a normalized wave function psi, the average value of the observable corresponding to A hat is given by the integral So in the last our lecture, we discussed that we can determine the average position of the wave function describing particle in a box using this expectation value equation, right? So this is the first postulate, number 4. So in a similar way, we discussed the particle in a box. We can always calculate the average value of the certain property that corresponds to operator A in here. But the average value is not the everything that you can say in a statistic way. And the other important property is the certainty or the variance of the measurement. So the variance, the sigma square, is defined as the expectation value of the square of your interest minus expectation value of your interest square. So this is the mathematical definition. So let's think about you want to measure the energy of the particle in a box system. So in that case, you have the wave function psi n, and you will have the energy eigenset En. So the variance of that system should be something like this. And you can easily realize that this is simply the square of the allowed energy level minus square of the allowed energy level. So basically this is just 0. So the variance of 0 is like very powerful result. So this means that there is no statistical spread and no uncertainty in this measurement. You always have the observable that is the one of the eigenvalues set. Okay, let's move on to the next page. Section 4.4, the commutator of the two operator plays a crucial role in the uncertainty principle. So I want to highlight the new terminology, the commutator. So it is always defined with two operators. So let's take a look at this quantity. So in the last section, we see that the quantum mechanics uses operator to extract information about observables from our wave function. And the natural question to ask is, does the order in which we consider these observables matter? Is it really matter? Does it really matter to take which measurement first? So like you want to measure the position and the momentum, then is it really important to measure the position first and the momentum later? Or momentum first and position later? Do we have always the same result for both situation or not? So that we are going to try to answer this question. So the order of operation is governed by mathematical property called commutation. So in our classical expectation, it shouldn't be matter, right? So like if you want to measure the position and the velocity, then the order is not really important, right? Because we always have the same result. But in quantum mechanics world, the things are quite different. So let's take a look at with the example. Oh, not example. Let's just discuss the definition of the commutation. So let's say we have two arbitrary operator, A hat and B hat, and they are said to be commute if their application is independent of order. That means when they are applied on the function fx with operator B first and operator A later, or A first on the function f, B later. So if they are commute, this result should be equal. In other case, if the order does matter, the operations are not commutative, non-commutative. So in that case, we are going to have a different result when we applied B first and A later, and A first, B later. The result might be different. Then the operator A and B are non-commutative. So we are going to define the commutator as the difference between A hat, P hat minus B hat, A hat. And they are denoted as square bracket A hat, comma, B hat. So you can easily imagine that if the operators are commutative, then the commutator square bracket A hat, B hat should be 0. Commutative. if the commutator is not 0, then these operators are not non-commutative. So if you have two commutative operators, then you can mix the order of multiplication. You can take the measurement A first and B later, or you can take the measurement B first and A later. It doesn't really matter. So everything is fine and very consistent with our classical expectation. But there are many quantum operator combination that does not commute. So in that case, like this. So in that case, their operation sequence is very, very important. So the result becomes different depending on you take the measurement B first or A first. So you might not really feel that is this really true? So let's take a look at the very good example. So we are going to discuss the position operator x and the x direction momentum px. So we know that the position operator is simply multiply x to the function, and px hat, this is defined as minus I h bar, and take the first derivative with respect to the x direction. So let's take a look at these two operators are commute or not. Example 4-7 is a really good example. So let's evaluate the commutator x and px operator. So when you want to figure out the result of the commutator, then you always apply the commutator to an arbitrary function. That means you always have apply this commutator to arbitrary function fx. So if you just if you follow this direction, then you might want to think like, okay, let's try so this is I want to emphasize that this is the wrong way. Many students think like that, so you cannot follow this direction. So let's write down the expression for that operator. So x, something like this for the first term, minus I h bar d dx, something like this. So for the first term, it might look okay, because this is just you are going to multiply x with the first derivative of some arbitrary function. Yeah, this looks fine. But what about this part? So you are going to take the derivative. So it should be applied for the wave function, right? But now you just take the derivative of the x function, right? So you missed some information from the wave function. So that's why you just cannot write down the operator, a series operator, and calculate the commutators. That will lead that will lead the very weird and wrong result. Okay, so let's put the arbitrary function fx here. So the result f something like this. So the first term is the x and the second term is something like this. X is here, x is here, p is here, p is here. And your arbitrary wave function fx is here. Okay, so the first part, minus IH bar x d dx fx. Okay, this part looks okay. And consistent with previous calculation. But what about the second part? So now you are going to take the derivative for the multiplication of x and fx. So your result might be like fx. Let's take out the constant. And you are going to take the derivative of the multiplication of functions. So fx plus x f prime x. So I mixed up two different notation to denote the first derivative of f, function f. So, but yeah, please understand. So these two expressions should be same, right? So let's rewrite this part. No, this part. Yeah, this part. I'm sorry. d dx fx. So you will realize that the very first term and the last term here, they should cancel each other, right? Because of this plus sign here. That means we only have IH bar and fx. So, okay, now we are ready to evaluate the commutator. So, we have two equations, this one and this one. Let's highlight these two boxes. So, the final result of applying the commutator x and px to arbitrary function fx is simply the multiplication of the constant IH bar with function fx. So you can say that the commutator xpx should be IH bar. So anyway, this is not zero. So you can say that the multiplication, the position x and the momentum of the x direction is not commutative. So it is very important when you measure the English expression mixed up in my head. So it is very important to take the which measurement first when you measure x, position x and the momentum p. Okay. So there is a slight difference IH bar depending on the first choice of the measurement. Okay. Okay, let's move on to the next page. And we are going to discuss Heisenberg uncertainty principle. So we are not going to derive that the relation between the variance and the commutator, but there is a mathematical expression that if you take the square of each property and multiply those variance, this value should be larger than or equal or larger than quarter of it is always larger or equal than the minus quarter of the expectation value of commutator A and B. So this sigma notation is the variance. So even though we are not going to derive that expression, but still we can discuss the physical meaning of this relation. So first case, if the two commutators are two operators are commutative, then that means their commutator should be 0. Then the right side of the inequality is 0. That means the multiplication of two properties variance, this should be greater or equal to 0. This means that there is no fundamental limit on how precisely we can simultaneously measure and know both property A and B, right? So for this inequality, we can say that both standard deviation can be 0. So we can have a really accurate value or measurement for A and B simultaneously. But more importantly, when the operators are not commute, when we say that these two operators are non-commutative, then the right-hand side is usually give a positive non-zero value. So there is some fundamental limit on the product of their variance, some arbitrary number k, which is larger than 0. That means if you want really highly accurate measurement, means the very small variance for the property A, then we cannot really go to 0, right? Because the multiplication of these two uncertainty is limited by the lower limit, positive number k. So that means the variance related to measuring property B should diverge. Goes to infinity. So let's apply this relation to our example case non-commutating operators for position x and momentum px, then we say that x and px is I h bar. So variance related to the position x and the momentum variance sigma px square, that is always equal or larger than the minus quarter of wave function multiplied by sandwiched. This commutator operator is sandwiched between wave function and this, this should be x hat and this should be px hat. So from the example we discussed above, this commutator should be IH bar. And now we are dealing with the normalized wave function, and this IH bar is just constant. So let's rewrite IH bar, and now we only have the magnitude of the wave function. And according to the condition for a wave function, and this integration should be just equal to 1. Oh, sorry. We need a square, right? Anyway, the square of the 1 is also 1. So that means we have a lower hand side result. So the multiplication of these two variance should be equal or larger than h bar square over 4. So if you take the square root for both sides, then the equation is reduced to the very famous Heisenberg uncertainty principle. So I'm not going to re-emphasize the physical meaning of this uncertainty principle, so you can go over by yourself. Okay, so I think we have to stop here because the next session also discussed a lot of things. So yeah, let's stop here and let's continue our journey on this Wednesday. Okay, thank you very much.